let's just say we start off with a rectangle, or it could be square, piece of paper, and we want to fold it up so that there will be 4 sides that will fold up nicely. So when you fold up the 2 edges, they fold up like this, right? You want the edges to be the same, which means that this side has to be the same as this length, right? You don't want them to be different because then one will be higher than the other when you fold it up. Ideally, after you've done the folding, it should look something like this, right? Like so, right? That's what we're doing. This length down here is the same as that one in there. This one over there is the same as this one here. Okay, now just consider this is a flat piece of cardboard or paper or whatever it is, right? When you cut the squares out of each corner, the minimum value that the square can be is obviously 0. You can't have a negative dimension, and we want it to have some volume, so it won't be 0. But the maximum they can actually go to, now think logically as well, if this is your x and it keeps on going, this is also the x, as the x gets bigger, at some point it will reach where? Halfway. Can it go beyond that? No, because essentially by that stage you're actually folding the whole sheet in half. So by that, there's already a limitation on the maximum value that x can take. Now let's just say this is a standard sheet of paper which is about, I don't know, I think it's 297 by, we'll go 240, right? So in this case, the maximum value that x can take is 240, and we already said that the minimum value was 0. And not 240, it's half of that, right? 120. Going this way, same thing again. As x gets bigger, right, you're slowly folding the page in half lengthways, but the maximum you get to is about, what, 148.5, but there's no point getting up to 148 because that's already exceeded the 120. Hopefully that makes sense. If you have a square sheet, then it's the same on either side, right? This is an important domain restriction because it will affect the answers that you will say in the applicable part of the graph later on. Now, using that, we can label the dimensions of the box that we've got folded up with the open top. So this is your x, the height, right, which is this one here because you folded it up. This is now going to be 297 minus 1x on one side minus another x on the other side. So that means minus 2 lots of x. So logically, the width will be 240 and also minus 2 lots of x, right? Now, we can use that to label the box that's being folded up. Now, how do you find the formula of the volume of a box? It is simply length, width, height. In this case, it is, we'll say your height is your x, put that up front. You have your 297 minus your 2x, then you have your 240 minus 2x, which does factorize. Right? So this one you can't, but this one you can. So that's a 2x now, because that's a common factor. This stays the same. This one becomes 120 minus x. That's your formula. Compare this, shift it a bit, to the standard equation of a cubic. So if you had y equals, we'll say, 2x and then x minus 1, x minus 2, right? Which actually you can just write them the other way around because the 2 negatives cancel anyway. What are the 3 x-intercepts for this? They would be 0, 1, and 2. Same with these ones. You can tell the x-intercept straight away. So for this case, it will be 0, not be x. Half of that, so it was 148.5 and 120, right? That's important because later on we're going to use that to determine the settings on the graph that we want, right? So now, and if we were to put these into the graphing section of the calculator, right? So it would be, remembering that as well, the CAS only recognizes the letter x when you're drawing a graph. So we had 2x times 297 minus 2x times 120 minus x. And what you'll see is essentially just a vertical line. The reason for that is because the graph that we've got is zoomed out so far that all you can see is like really close, and just the first part of the graph, and it looks like essentially a vertical line. This is where your basic concepts comes into play, right? So if you were to draw this thing here, using your basic theory again, you know it's a cubic, right? Because it's x times negative x times negative x again. You know it's a positive cubic. Plus x times negative 2x is negative 2x squared, times negative x is positive 2x cubed. You know the x-intercepts, right? And the y-intercept, well, it's going to be 0 because when x is 0, y is also 0. So it will look something like this. Where this is your 0, 120, 148, 5. Alright, so we would expect, we cannot assume because it's a cubic, but we would expect the maximum, this point up here, to be roughly halfway. It's not actually halfway because it's not a symmetrical graph. Be careful of that. For a cubic, it is not symmetrical. You cannot assume it is. A parabola, you can. A cubic, you cannot. But we can estimate. So if we were to say, roughly when x equals 60, we would get this maximum value. So what you would do is you go to the calculator section of the CAS and sub in x equals 60 into here, here, and here, and then see what you get. So you do that, you go back to the home, go calculator. So 2 times 60, we know that is 120, times 297 minus 2 times 60 again, 120 times, and that's just 120 minus 60 times 60. You can see it's a really, really big number. On the calculator, it will show it, on the graph anyway, it will show it with exponential. So it's 127, no, 1.27 million, right? Remember these dimensions, well, this one is actually in millimeters, so your graph will also be really, really big numbers. Okay, so now what you do is, when you go back to the graph, you want to set it so that the axes are proportionate to what we expect it to be. Okay? So you go menu, window zoom, Windows settings, and you can manually set them. If you were to use the zoom out feature, because you've got to get out to 1.27 million, you'd be zooming out like 50 times, and that's just a waste of time. Far better if you have a better idea of what you should be setting, then you can actually set the axes manually and zoom out to that straight away. Right? So the x values, we said we only want from 0 to 120. So let's be proportionate, negative 50 or negative 40 up to 150 then, something like that. Right? You don't want it to be on the edge of the screen. You can if you want, but I like it to be in the screen, not fitting right on the edge of the screen. And the y values, we have to go up to, we'll say 1.5 mil. So we'll go from negative half a mil and up to 1.5 million. And there you go. The graph fits nicely on screen because we've set it using our basic theory rather than wasting time. Now note that it has the e's here. That means that's times 10 to the power of. So you actually just move the decimal point 5 times. And then if you want to find the maximum as well, you can see that the graph itself is not symmetrical as we said. All right? So the maximum does not occur when x equals 60, but it's close to that. To find the maximum, you just use the usual calculator feature, which is analyze graph maximum. And again, it has to be between two boundaries, so just anywhere to the left of it, right? Click once, move to the right, and as it finds it, there it is. That's the maximum. When x equals 44, the maximum is, in this case, move the decimal point 6 times, so it is 1,397,000 and so forth, as the actual volume. Pause. The example I'd like to do is for a cylinder. All right. If you were to measure the dimensions of a standard can, and I'm not saying this is any sort of heater whatsoever at all, but a can, well, we know that it's 375 mils, right? Which using conversion is 375 centimeters cubed, right? Is actually made up of about, if I remember correctly, a 250 centimeter square sheet of aluminium. Right? So if you were to say this is equal to the total surface area of the can that's used to make the can you work out dimensions of the can that would actually give the maximum volume and what that maximum volume would be. Don't use this to start working out anything. You're using this. So think about a manufacturing company has this much sheet aluminium and they use it to work out what size can they would actually make to sell their product. Okay, so start off with what is the surface area of a cylinder. So obviously that's not a written can, but what we're getting at is that that's the radius, that's the height, right? Again, you do not need to remember formulas in maths, it's about how you apply them. The formula for the surface area, and we're simplifying this down. Yes, we have the little ring thing on the top and it's got the corner on the top as well, but we're simplifying it down just to get an idea, right? So it's made up of two circles, the bottom and the top, and the circumference area around the side, which is your circumference of the circle times the height, right? This simplifies to taking out the 2 pi r plus h, right? And we're saying that that's equal to your 250, right? Can you get the h by itself? Because you cannot have two different variables in there. Let's make it by just the one. So you divide this over, right? And then subtract the r. If you were to simplify this, right, so that's your height in terms of the r. Now, consider what is the formula for the volume of a can. It is the area on the top times the height. So, pi r squared times your height. But we know the height from here. So we're going to put that into this formula. So the volume is then pi r squared times your 125 over pi r minus the r. Expand and simplify. 125 pi r squared over pi r minus pi r cubed. Alright, these cancel. Alright, if we just factorize the r back again, which we probably shouldn't have done in the first place, but now, again, go back to your basic theory. Looking at this equation that we've got for the volume. If you had a simple equation, your y equals x times 4 minus x squared, how does that look? When the squared is inside, it's essentially dots, which means that if we factorize this further, 2 plus x, 2 minus x, it is x times negative x squared, which means it's negative x cubed, which is a negative cubic, right? The intercepts are at 0, and then opposite the square root of this, plus or minus 2, right? So it would look something like this. This one just so happens to be symmetrical, so you probably can use the middle of the graph. Same with this one then. So we would know, and this is where the calculator comes into play. Sorry, not the r, but the r intercepts, or in other words, x intercepts in this case will be 0, and then plus or minus square root of 125 on pi. Okay? And again, when we're drawing it, we cannot use the letter r, it must be the letter x. So, let's draw that. So we have x times brackets minus pi, use the actual pi function, times x squared. And again, you just see 3 vertical lines, which doesn't help. Alright, so we want to zoom out to an appropriate amount so they can make it fit on screen in one go. So again, we would expect, if we change these ones to negative root 125 on pi and positive root 125 on pi. Let's approximate that. Okay, so go to the calculator. So square root Well, it doesn't have to be exact for us, we'll just go 3.14. So 6.3, so we would expect this point to be roughly about 3. Right? So I substitute that into this, so we get 3 times 125 minus 9 pi. Control enter there. 290. Alright, so I think I may have used the wrong dimensions for CAD, but anyway. So again, so let's set the axes. We only want to go up to 3. Oh no, 6. So we'll go from negative, we'll go negative 4 up to 10, and that's it. Think logically as well. The radius we're getting is roughly about 3, which sounds about right. When you think the can is about this big, the radius is about 3. Okay. Y, what do we get? So we'll go negative 50 up to 350. And there you go. Alright, so no, it's not actually symmetrical this time, again. So just be careful with that. You can never assume that it is, unless it's a parabola. The maximum, again, between those 2 points, I have used the wrong sheet metal size. Occurs when the radius is 3.64, the maximum volume will be 303. So imagine if it was, right, to this one, it would essentially be a relatively fatter can, 3.64. Then you can work out the height, right? So we did 3.64. Remember the height was this one here, right? So we go back to the calculator. It'll be 125 divided by, what do we get? 3.64 pi, and then that minus 3.64 is the height. 7.3 centimeters, which is only about that high. Now just consider the ideal dimensions of a can to maximize the volume is actually very short and very fat. Right? Now try to think logically in terms of the marketing department of a company. Why would they not give or produce a can that maximizes the volume that they can give to the customer? A couple of reasons. One, it means they're giving more product for the same price, right? And the second thing too, consider the actual size of a human hand, right? If you make the can too big, it's difficult to hold. Yeah, you also got to think about that too. The energy drink cans these days are even thinner and longer, which suggests what? They'll probably even hold less volume. But why do they do that? To make it more aesthetically pleasing to the customer. Right? So now as math students, you know that, oh, no. They're being very smart. That's not actually the maximum volume they could have created or produced using that amount of sheet aluminium, but they've done this for these other reasons instead. Hopefully that helps.